You're here because you want to master electrolytic cells with a University of Cambridge graduate. Let's begin. Now, a lot of students ask me, Brendan, why is it so difficult to apply my electrolytic cells concepts in order to answer the question? Well, I'm here to break it down for you and help you understand that electrolytic cells is really not that difficult once you understand the different components of the whole electrolytic cell and understanding each of the reactions that happen within the electrolytic cell. If you want access to my free notes, do check out the link below so that you can download a copy of them as you watch my lecture. Let's start by looking at what an electrolytic cell comprises of. On a first glance, when you look at an electrolytic cell, you realize that the main difference between an electrolytic cell and an electrochemical cell is the use of the batteries. Since we have batteries over here, we're mainly using electrical energy and converting it into chemical energy. By looking at the batteries, you would know that which side has the negative charge and which side has the positive charge. The shorter end over here would be the negative charge, and the longer end of the batteries would have the positive charge. Since the left side has the negative charge, you know the electron on the left has the negative charge, and vice versa. The right side has a positive charge, so the right electrode will have a positive charge. After deciphering the charges, you'll be able to tell which side is the cathode and which side is the anode. So the negatively charged side will attract cations over here, and therefore it is called the cathode. Whereas the positively charged side, right, attracts anions because anions are negatively charged, so therefore it's called the anode. Now from here we'll then know that reduction always happens at the cathode and oxidation always happens at the anode. So how do I remember this? Well, you can always remember this acronym over here, that red cat, right, which means reduction happening at the cathode, and anox, which means anode has the oxidation. Now, how do I determine the different reactions that happen at each electrode? Well, you can follow these series of steps, and by following this, you definitely understand what is happening within the whole electrolytic cell and be able to answer your questions more efficiently. Step 1, you're going to look at the ions and molecules in the electrolyte. So you need to clearly and look closely at the state of the electrolyte, whether it's molten or aqueous. So take for example, if I have NaCl liquid, which is the molten state, then definitely in the electrolyte there will only be Na plus and Cl minus ions. Alright? Versus if you have NaCl aqueous, for example, so sodium chlorine, the aqueous state, then not only will you have Na plus and Cl minus ions, you also have water molecules inside as well as a small concentration of H plus and OH minus as well. Now step 2, you want to look at the potential ions and molecules at each electrode and analyze using the E0 value to determine what reaction will happen at each electrode. So you first have to sort out the different cations and different anions and to which electrodes they go to. So the anions will go to the anode, whereas the cations will go to the cathode. And then you have molecules like water, for example, that could participate in both of the electrodes. Next, if you look at a cathode, for example, where reduction occurs, you want to see the species with the higher E0. Now, the species with the higher E0 value from the reaction would be more readily reduced and therefore would more favorably be reduced compared to other species within the electrode. Now, at the anode, you want to see the species with the lower E0, because the species with the lower E0 for their reaction are more readily oxidized. Do take note that you always want to think about H2O whenever the electrolyte is in aqueous state. And this is because H2O is in really great abundance in the whole electrolyte. And usually in most of the cases in aqueous states of the electrolyte, they would participate in the electrode reactions. Next step, you want to look at the concentrations. So this rule typically applies for your anions at the anode. Specifically, it's usually for F minus, Cl minus, or Br minus. When they are in higher concentrations, they would usually oxidize more favorably compared to H2O, even though the E0 would say otherwise. And do take note that for large anions like your NO3 minus or your SO4 2 minus, a higher concentration usually is not enough for it to be oxidized, and usually water would be more favorably oxidized in this case. So let's take a look at this example over here. If you look at this half equation over here and this half equation over here, these two half equations represent the oxidation of water if you read from the right to the left, or the oxidation of Cl minus if you read from the right to left for equation 1. Now, if you look at the two E0 values, you will see that since water has a lower E0 value, this is usually oxidized more favorably. However, when you have a concentrated solution of sodium chloride, for example, when you have more Cl- ions in high concentration, this will shift the equilibrium, right, to the left. And this would make the E0 of equation 1 be lower than the E0 of O2H2O. And this would make Cl- become more easily oxidized than your H2O at the anode. Last step, you always want to consider the nature of your electrode. So if your electrodes are inert, for example, they are graphite or platinum electrodes, the electrode will not be involved in the reactions. But if you're using an active electrode, for example, a metal electrode that is very active like zinc or copper, they are most likely favorably oxidized in the reaction. This is because your metals generally want to become ions and therefore are more favorably oxidized. But you can't always be too sure, so as always, just take a look at the E0 values and they would paint the full picture of the whole story. Next, we move on to calculations in electrolysis. So in calculations, you just want to know about two equations over here. Q equals IT and Q equals to NF. Q is the quantity of charge, and I is the current, and T is time in seconds. So taking note of these units is very important to get the correct units. And Q also equals to NF, where N is the number of moles of electrons going around in the circuit. Usually you'll get this number of moles by balancing the two half equations at each of the electrodes. And F is Faraday's constant. Most of the time, you don't need to work out what Q is. Rather, you can just say that NF equals to IT or IT equals to NF, vice versa. The first application is anodizing aluminium. What we would do is we would attach an aluminium object, for example an aluminium spoon, to the anode. And we can have an inert cathode and dip these two electrodes into a sulfuric acid solution. At the cathode, we'll have a typical reduction of H plus because we're using sulfuric acid, so H plus would just be reduced to H2 gas. But what's interesting is what happens at the anode. Now at the anode, you have a reaction over here that happens first, which is just the oxidization of water. But you also subsequently have the oxidation of aluminium, which is the material of the spoon, for example. And this aluminium, when oxidized, will give this Al2O3, which forms this protective layer over the spoon. And this is what preserves the material of the spoon and makes it long-lasting. Now I would advise that you memorize these equations because they could easily be tested and you'd be, in general, asked what is anodizing aluminium, and you have to draw a setup and write the equations that happens at each of the electrodes. The next application of electrolysis is the purification of copper. How we'll set this up is that we'll have a pure copper cathode and we'll have an impure copper anode where it has multiple other materials such as zinc or even aluminium. These are some common examples. And we'll dip these two electrodes into a copper 2 sulfate solution. What's going to happen at the cathode is the copper 2 plus ions within the electrolyte is going to be oxidized favorably compared to water into copper solid. So I won't be surprised if my copper cathode grows in size. Whereas at the anode, it is primarily the oxidation of copper 2 plus. However, before this oxidation of copper 2 plus, actually, if you compare the E0 values of copper and zinc, you'll realize that zinc has a lower E0 compared to copper, and therefore it's actually more favorably oxidized first. So what is happening at the impure anode is that your more reactive or more readily oxidized metals, for example zinc over here, will be oxidized first, and then follow up by copper, and then follow up by metals that are not really favorably oxidized. Now, since copper is in very high percentage, you'll actually oxidize some copper, and for the very non-reactive metals, for example gold, they will actually just drop off the anode, and sometimes you'll see this anode sludge over here that comprises of the less oxidized metals. In summary, electrolytic cells is really a simple topic once you understand the different reactions that can happen at each of the electrodes and break them down. I would advise for each of your electrolytic cells questions, you just run through each of the different steps that I have listed so that you can find out what reactions happen, and from there, use that as a base to answer the rest of your questions. If you want to enroll in my chemistry class, be sure to also hit the link below so that you can book a free call with me and I can run through any doubts and clarifications you may have and even go through a test paper that you've done previously for you for free. And I will show you why my lessons are the best fit for you. If you like this type of content, be sure to hit the subscribe button and hit the like button as well so that you can get more frequent updates about my free content. I'll see you in the next lesson.